Good afternoon, good morning, wherever you are. This is episode 59 of Codebase Alpha, and we're on part 3 of looking at software synthesizer projects using RackAFX and C++. So where we left off last time, we kind of half completed the low frequency oscillator class that we were building, and we were just kind of half completed the pitched oscillator class, the one that actually we hear. Remember, with a low frequency oscillator, we don't actually hear that. That's used as a control, so it modulates other things. And we're going to have eventually our synthesizer will have what we're going to call a modulation matrix, and which means we'll be able to tie the LFO or LFOs, if we have more than one, which we may do, into lots of different kind of controls. So filter cutoffs, envelopes, pitch, all kinds of things. So we're going to have kind of really kind of flexible way of linking our modulation controls to our oscillators and to the other kind of effects and devices that we're going to have modeled in software. So just to kind of recap, we're working from a book called Software Synthesizer. It's called Software Synthesizer Plugins with C++ by a guy called Will Perkle, and we've used his stuff before in the when we were writing plugin effects with Juice. So that was a different book that was writing digital audio effects with C++, and it's a really kind of usable kind of books. They've got a lot of theory in them, but if you kind of trying to skim the theory and then save it up to learn later, you can pick an awful lot up from doing the practical work, which is what I wanted to do on stream. So I decided that what we'd do is we'll work through some of the projects that are presented in the book. And we're using a piece of software called RackAFX, and we're using version 6. It's really important that if you want to follow along with these projects, it's version 6 of RackAFX we're using. There is a version 7, but it's not the one we need for this particular set of projects. At some point in the future, I may look at converting the software we write to version 7. A lot of the classes that we are writing are going to be kind of they're just transferable between any system. They're not in any way tied into RackAFX at all. So our oscillator classes, our envelope generator classes we're going to build, our LFO class, they're all independent. They're completely reusable C++ objects. But the controls and the GUI prototyping software that we're using, RackAFX, and it's also the plugin manager. That is what's kind of tied into the version 6, and version 7 uses a different kind of API model. So there's some conversion work to do, and I haven't really thought about doing that yet. But we'll do at some point. One thing I did do is convert the Juice project we did for the dimensions delay effect. I converted that over to RackAFX 7, and that was a breeze to do. So I'm really hoping that we can kind of use RackAFX 7 and the API, which is called ASPIC, going forward. But let's just pop over to the code right now, shall we? So this is RackAFX, and we've got nothing loaded in so far. So basically, RackAFX consists of a whole bunch of GUI controls. We've got all these sliders here. We've got some button banks here. We've got what's called an LCD alpha wheel control, which is basically contain, I think, it's 1,024 separate controls within there. And we have some test equipment in here. We've got an oscilloscope and spectrum analyzer built in, and we've got a load of VU meters and stuff like that. So what RackAFX will do for us is actually create the skeleton of a project, and we've already done that for our project, which is called NanoSynth. And NanoSynth is basically going to be a test bed. We're going to test all of our C++ objects that we're building using this synthesizer plugin, and then we're going to build other synthesizer plugins based on it, but we'll always come back to this to test. Okay, so let's have some music while we're kind of thinking about this. So this is Relax Daily, which is what I really like to listen to when I'm coding. This particular, there's 3 tracks on this loop, and they are completely free to use, royalty free on streams and YouTube, whatever, but there are hundreds of other tracks. which I also own, but I can't play to you on air. I also use music to code by, music to flow by, whichever of those two, and once again we can't have that on stream. But having some kind of music which is unchallenging, you haven't got to listen to, and it's in the background and it has the right rhythms in it, kind of helps you concentrate, and that's really important for me on stream where it's quite difficult to actually concentrate. So let's just minimize this here, and this is the code we've been writing. So this is our QB limited oscillator, our quasi bandwidth band limited oscillator. So if you were with us in the previous streams, you'll understand that we are using, for our pitched oscillator, the audible oscillators, we're using a method of modeling analog oscillators. We'll go into the details of that if we have time or on another stream. What I want to do today in this stream is try and get some sounds out of our plugin. So there's a couple of things I want to do before we start. So last time when we built the low frequency oscillator, we had this do oscillate method that we created, and over in the header file we had this prototype, and you can see it's subtly different. This quad phase output doesn't have the default value of null on it. It's a pointer. It's a pointer to a double value, and we're using this Hungarian notation only because that's what RackAFX uses. So we're kind of falling into line with it, even though I personally don't like Hungarian notation. What I thought the best thing to do here, because they're different, the signatures are different, I'm not 100% sure what effect that's going to have. So what I'd like to do is move the definition of a do oscillate into the header file. So what I'm going to do is I'm going to grab the whole of it like that, and copy it and delete it like that. Now I'm going to just undo that because I think I've grabbed too much. So let's try again. So from inline there, all the way down. To there. Get rid of that. Okay, we're going to cut that, and that means that's okay. And then we're going to pop across into the header file, and we're going to just paste that in there. And I think we may have to have, I think that's right, virtual inline double, and I don't think we need that anymore. Okay, so that seems okay to me. Let's just save that. Okay, and let's just do a build to make sure. What we'll do is we'll build from within RackAFX. So I can click the rebuild button. Let's make sure we build. Now we've got no viewers at the moment in chat, so I'm not too worried about that. We've got C# Fritz on at the same time, so I'm not really expecting to get viewers. So it's built. We can't. A small stream like mine can't compete against the heavy hitters of the live coders team like Jeff Fritz. So we're just going to carry on anyway, and all this will be available on YouTube anyway. So you won't have missed things if you actually don't catch the stream. Okay, so we build okay. That's good. Okay, so that's that one, and we're going to do the same with our oscillator. Now the oscillator we didn't actually get to write. So what did we get to write with the oscillator? The pitched oscillator over here. Here we are. So we didn't actually get to write the function itself. But what we're going to do is grab it and we're going to cut it out, and we're going to put that across into the QB limited oscillator header file as well. And we're going to pop it into there. And what I'll do is move these pieces up there. Okay, so in our quasi band limited oscillator header, now we have the outline of our do oscillate class, and we can get rid of this. Okay. So what else did we do last time with our quasi band limited oscillator? We created a do sawtooth, a do square, and a do triangle method. So these are going to produce a nice, well, sawtooth can be used to create three different types of sawtooth wave. What's called a trivial or a raw sawtooth wave, which will have lots of aliasing in it, but also we can get some analog modeled sawtooth waves out of that, and those are based upon a system called BLEP, which is band limited steps. So what we're doing there is we are smoothing out the discontinuities in a sawtooth and indeed in a square wave. We get the square wave by adding sawtooth waves together, and by doing this we reduce the aliasing, because we're not jumping immediately from, in the case of a sawtooth wave, from -1 to +1 or +1 to -1 with nothing in between. We're kind of pretending there's samples in between there to smooth that transition, and that just basically almost eliminates most of the aliasing. Brendonius, welcome to the stream. Good to see you. Didn't expect anyone in the stream today, as it's a pop-up and we got Fritz up against us. So I'm just trying to get some of this code written and sorted. I see he's not sharp. No, it's C++. This. Okay, so we've got that moved here, and I think everything else is okay. There's our triangle wave generator. I just wanted to explain some of the triangle wave generator that we probably didn't cover last time. It's this thing called P. It's a pointer to something called Z register, and we're going to be referring to that in the next part where we do the do oscillate command. In this, this includes a step where we do differentiation, digital differentiation, and differentiation. You know, if you think back to your mathematics classes at college or university, it can be quite complex. But in this case, a differentiation between 2 points in a digital a set of digital samples is really easy, because what we're doing is we're basically taking the current sample and the previous sample and figuring out what the slope of a line between those 2 points is, and the slope of the line is the differential of it. So that's when we say we're differentiating here, it's really a simple operation. All we're doing is saying take the current value and the previous value, work out the slope of a straight line between them, and that is the differentiated value. So really easy. But we're going to be coming against this Z register, and I think in the back in the Juice C++ streams that I did covering audio plugins, we did talk about Z, and basically the Z register is simply a delay. So in this case, it's a delay by one sample. But we can kind of go over all that again when we start talking about block diagrams, and we analyse what our plugin synthesizer looks like through block diagrams. Okay, so let's go back over here and code some of this. So so what we need to do here, so we're going to get rid of this code for now, because that was only there to make it compile. So let's think. So the first thing we need to do is to figure out if we've got a MIDI note being played or not, and we've got a member variable called m_note on. It's a boolean that tells us whether a MIDI note is on or off. And if you remember, in the very first episode of this series, we created some logging for the MIDI keyboard I have, so that we know that when we press note on, note off, those messages are being transmitted and being picked up by our plugin. So basically what we need to do is here say if that value is if it's not true, so let's just put the not operator in front of that, then we're simply going to return 0. There's no sound, and this is a double value, so we're returning 0.0, in other words, as I say, silence. So if there's no note playing, then we return silence. The next thing we need to do, and we always need to do this, is to figure out if our modulo counter has wrapped. So remember from the last time we talked about modulo counters. A modulo counter is simply a counter which goes up from 0 to +1 in certain increments, and when it exceeds 1, it wraps round to 0 plus the amount by which it exceeded +1. 1 in other words, So it goes from 0 to 1 and wraps round by the amount it exceeded the number 1. And the increment value is worked out from the frequency of our oscillator divided by the sample frequency. And in this case, I believe the sample frequency we're going to be using throughout is 44.1 kilohertz, which is the CD recording sample frequency. Okay, so let's just define a double, which is going to be our D out. This is our output value. In fact, what we're going to do, we're going to define that above, and we're just going to and we're just going to return D out at that point. Make it nice and neat. There we go. Okay, now we need to check whether we've wrapped or not. So we've got a Boolean value, and it's going to call bwrap. We have a function, a built-in function, which is going to tell us whether our modulo counter has wrapped. And it's exactly the same one we used last time. It's called check wrap modulo. So this is what we always do. Has our modulo counter wrapped or not? Okay. Now we need to calculate what our modulo is going to be. Now here we're going to introduce something which I'm hesitating whether to introduce this at this stage, but it's the idea of phase modulation. Our current system isn't going to do phase modulation, but when we do our modulation matrix in a future stream and we start getting a really kind of functional synthesizer with lots of different options, then phase modulation is one of the things we want to do. And phase modulation is where we take we modulate the actual phase angle of our sine wave or square wave, whatever. So we move it to the left or right in respect to other waves, and that basically causes destructive interference and constructive interference and gives us some interesting sounds. So phase modulation, it's a thing that synthesizers do. Digital synthesizers do that, analog synthesizers do it, so we should probably do it as well, but we haven't actually coded a way of actually modulating the phase yet, but we're going to put that in. So phase modulation for the future. Okay, so we need a double now, which is going to be our modulo counter, which is it's incrementing between 0 and 1, but it's going in floating point values. Increments of floating points. So our calculated modulo is going to be our member modulo, which is MD modulo, and we're going to add the value of our phase modulation in there, which is MD phase mod, and we're also going to check once again if we've wrapped at that point. So we're going to use a function called check wrap index here, and we're going to pass that modulo into that decal modulo. So we're not going to use this yet, but that bit of code is there just for the future when we want to use it, so we don't have to remember to come back and actually code that. Okay, so we're now ready to do our big switch statement. If we go back to our LFO, you can see that do oscillate, it has a similar kind of setup, but here we do the check modulo, and the LFO has different modes, like one-shot mode, synchronous mode, and free running modes, which I explained last time. But the majority of this method is actually a big switch statement. So based upon this value of M waveform. So what waveform are we trying to produce out of this time out of our pitched oscillator? So let's have a switch here. Okay. So we want to produce, the first one's going to be sine. Now it's going to be basically exactly the same as our LFO. So let's find the sine. Here's the sine. Let's grab that piece of code and use that. So I'm just going to indent that. And this is going to be capital SINE because we're working on the pitched oscillator. We use lowercase for our LFO oscillator values. And we're not going to have any quad output here. You'll notice we do have this quad phase output. Actually, we should rename that as what should we call it? P aux output. And we're going to use the auxiliary output when we have stereo oscillators, but we're not going to have a stereo oscillator in this case. This is a monophonic oscillator. Okay, as monophonic as in it's not stereo, it's a mono oscillator. So we're just going to copy the value of D out to this P aux out, but we need to. It's not. We're not using quad phasing like we did in the LFO. Okay, so that's that. So now we have case. We're going to have SAW 1, case SAW 2, and case SAW 3. So these are the three different forms of sine wave, sawtooth wave that we can produce. In this case, D out is going to be equal to do sawtooth, and we're going to pass into that our the calc modulo and our increment, which is a member variable, minc, like that. Okay. So that's as simple as that, because we've already written the method which creates that. So what's your question, Brendonius? You're thinking there. So now for a square wave. For the square wave, it's very similar. We've already got a do square, so we can actually copy this piece of code here and change this to do square. Okay, and finally we've got triangle wave. This is slightly more complicated because we actually have to do this twice. No specific question, just thinking through the stuff you're doing. It's actually well, yes. So it's kind of outside mine as well in many ways, but it's something that I'm actively trying to learn. So a lot of it's still percolating through my brain about what we're doing. I've got a pretty good idea of what the code's supposed to look like, and I don't know what it's going to sound like. That's the kind of the exciting bit. I mean, I love the idea of making your computer. Yes, right. So we've got that changes, so we can control that. So, but yes, we're in the thinking mode at the moment. Oh, I see. Right, you're making the if you had a red grabber, yeah. I love the new emotes. So I've just ordered a new emote. Actually, it's an Alf saluting. So hopefully, Night Artist 86 will come through in the next week with a nice new Alf emote. Okay, so triangle wave. So this is slightly more complicated with a triangle wave. How to explain? We have to increment the modulo twice because of the algorithm which generates the triangle waves. It's a rather more complicated algorithm. I don't want to go into the mathematics behind it in this stream. This is going to be a purely practical, getting a computer to make a noise kind of stream, really. But we'll come back to it. So what do we need to do here? So first thing we need to know if we've wrapped our modulo counter's wrapped. If it has, we need to sort this indenting out. I don't like the indenting it does. So if our modulator counter wrapped at this point, then what we're going to need to do is to increment our square wave modulator. We have a square wave modulator which we used in over here, the D square modulator, but we do have I believe we should have a member variable to store it in. So it's going to be a that's it, square modulator. So DPW is the algorithm we're using, and we're going to simply going to increment that like that. Okay, right, and then we can get our value of D out, which is going to be our do triangle, and we have to pass in our D modulo, which is our D calc modulo. Remember, this is the one that's been affected by phase modulation if we have that. Then we need to have our increment, which is MD inc. We need our frequency, which once again is held in a member variable like that. We need the square modulator, which is our once again our member that we just used, square modulator, and then we need to pass in our Z register. Now, what's the Z register? It's going to be a pointer to it, I believe. Maybe not a pointer. It's going to be a dereferenced memory address, isn't it? So ampersand and then MD, value of our Z register. Remember, the Z register is simply the sample before this one we're processing. All it's doing, all the Z register do is says what was the previous sample, and it holds it for one kind of one pass through the algorithm. So it's always one behind. If there wasn't a previous one, it would be 0, because obviously there was silence before the note played. So that's that, and we can then break on that. Okay. So at that point we need to do our white noise and pink noise. So case noise. Once again, this is going to be identical to our LFO. Noise is noise is noise. So let's find our, where's our noise oscillator? So I believe it's going to be this do white noise. We'll try that out. I believe that's correct. So D out is going to equal that. Break on that, and then we've got a pink noise. So pink noise is simply a higher frequency. So it's noise which is richer in the higher frequencies. So hence pink, as in red shifted. That is going to be similar to whatever we got over here as well. So I believe it's going to be that, a pink noise sequence. That should be correct. So D out we equal that. We can break. Okay. So that should be the end of the case statement. Okay. At that point we want to, as we've passed through this, the note is still on, we're passing through this method, we want to increment our modulo counter, and we have a function which does that, inc modulo. Once again, it increments the modulo counter by a double value, which is the ratio of the frequency of the note that's been played divided by the sample rate of 44.1 kilohertz. So if we play a note of 5 kilohertz, it's 5 divided by 44.1 basically. Okay, and this is where we do the double increment. So if we got a triangle wave, we need to do a double increment. So we can say here, if it's the waveform, U waveform, because it's a unsigned integer, or in other words, it's a an enum. Then we need to inc our modulator again, increment our modulo counter again, and that's dictated by the algorithm for triangle waves. So if that equals try what's the algorithm for triangle? Requires, okay, so got that, and now we want to know if we've got anything in this auxiliary output pointer, if there's a value in there. By default it will be null, so it will be a mono oscillator, but if there's a value in there, we want to copy the D out into it. So we can say if that, then what we can say then is the pointer Paux is equal to D out. Okay, so D out, then we need to multiply by the volume, which is basically the amplitude of our output. So that's going to be the amplitude there, and if we have some amplitude modulation going, we need to multiply by the amplitude modulation factor as well, which is this one. And then what we can say simply is that at the end of the whole method, we're going to return that same value. Okay, so what I'm going to do, I think, is I'm going to calculate this value above. No, I'll leave it as is. I'll leave it as is. Okay, let's see if we build. Let's save, go over to RackAFX and hit rebuild. I'll grab a drink while that's happening. Wow, we built. Okay, I'm going to I think we can just load it at this point. Maybe we can't, maybe we have to run it first. No. What did we do last time to do this? We rebuilt. Oh, we picked debug, that was it. Make sure we build okay again. Okay, hit debug. What it doing? Oh, we need to do it more. We haven't quite got there yet. Okay, I'm ahead of myself. Okay. Right. Let's think about the next stage we need to do. So let's bring up our Solution Explorer. So we built our basic oscillators. What we need to do now is we need to do something with the plugin. So nanosynth.h. So this is our actual plugin. We build at least, which is good. So in here we should have some places where we can start to define our variables. So these are all the functions which RackAFX builds for us, and what we need to do is to actually create some variables in here. So I'm just going to take a couple of seconds break. There's something happening just over here. I need to kind of take care of. Hang on a second. Sorry about that, just had to take care of something. Okay, so we're back over here. So these are the values which have been added by RackAFX for our prototype user interface, and it says here add your code here. So that's where we're going to add our code. So if you cast your mind back to the very first episode of this series, we said we were going to build a synthesizer which had a number of features. It was going to have at this stage, a single low frequency modulation oscillator and two pitched oscillators, which we're going to run in parallel at the same time and detune from each other to try and give a fatter sound. Okay, so what we need to do first is to actually define those. So what we can say is they're going to be of type CQB, so we're going to need to bring our oscillators in first, aren't we? So let's go back to the top here. We need some include files, so include, and we're going to have, so it's hash include, we're going to have LFO .h for our low frequency oscillator, and we're going to have a hash include of quasi band limited oscillator for our pitched oscillator. So now down the bottom here we should be able to find that class CQB limited oscillator. We're going to call that M_C os1, C for class. No, we'll just call it oscillator 1. I do rebel against this Hungarian notation. And we want a second oscillator, oscillator 2, and we're going to have a low frequency oscillator, CLFO. This is going to be LFO. We'll have LFO 1 as well, because we're going to have more than one low frequency oscillator eventually. And then we want a function. This function is going to be a void function. It's going to be called update, and it's what we're going to use to when we change our GUI controls. It's what's going to actually reconfigure our oscillators and LFO to actually to respond to that. So that's pretty much all we need to do in there. Let's remove these from the list at the top. We want nanosynth.cpp now. Let's go and have a look at it. So this is our actual class file. Now there's a bunch of things we need to do with every RackAFX project. There's basically 10 functions that we need to consider and work on. The first is our constructor. Our constructor, we need to set the flag which is going to capture all MIDI messages, and we've already got that set. Okay, we've got our MIDI channel set to all MIDI channels, so we're capturing data on all MIDI channels and all messages. One thing I'm going to do is change this flag to 0, so we're not logging MIDI messages, because that will slow us down. Okay, so we've got that in there. The destructor, I don't believe we need to do anything yet. So next one is prepare from play. So we got an initialize. This is like for one-off initializations, which we don't do within the constructor. And then we want prepare for play. And you notice helpfully we get the kind of all the code, the comments in here to tell us what to do. So this method is called by the client. In this case, it's going to be RackAFX. It's going to call it while we're still in development. After the play, after play is initiated, but before the audio starts streaming. So here we can do things like buffer flushes. We can per run initializations. We can check these variables and use them if we need it. So these values are available to us, including the important one, the sample rate, and things like bit depth and number of channels will be important at other times. So these values, it says, only valid while we're in the scope of prepare for play, and also ProcessAudioFrame, because in between they might have changed the wave file, the sound file, might have changed oscillators or other things. And it says if we allocate any memory in this function, we must destroy it in the destructor. But we won't. If we do allocate memory, we won't be using functions like malloc. We'll be using smart pointers and stuff like that. So we won't necessarily have to worry about the destructor part of it. Okay, so what do we want to do in prepare for play? Well, I think there's basically 3 things we need to do. We need to set up our sample rate, and we've got that there. So remember, the sample rate is really important to determine the modulo counter increment. So we need to set that. We need to create our 2 oscillators, and we need to detune the second oscillator a little bit from the first one, so we get, let's say, that fat sound I'm trying to achieve. And then we need to update all our variables. So let's have a look how we do that. Okay, so let's update our oscillator sample rates first. So oscillator 1, on there's a set sample rate, and into that we're going to pass in this value n sample rate. We know this value is available to us at this point, and it's valid at this point because our comment above says so. We can do that 3 times now. So oscillator 2 and an FO1. So remember that oscillators, whether they're pitched oscillators like the first 2 or low frequency, they're all inheriting from our base class, our oscillator base class that was provided to us by the project. So what's next? So we need to detune oscillator 2. Okay, so oscillator 2, and there's a function on here. Well, there's what should we say? There's a variable, an attribute it we've called, I guess, or a property called sense. And we're going to detune our oscillator. So normally this would be 0, which means it would be whatever frequency F0 you put into the oscillators, that's what's going to come out. But we're going to just, by a very small amount, we're going to detune this from oscillator 1. And this is 2.5 cents. So if you imagine that a semitone, in musical terms, a semitone has been divided into 100 sub sections, we're going to detune oscillator 2 away from oscillator 1 by plus 2.5 cents. 2.5 units in that 100 between 2 semitones. Detune oscillator 2 by 2.5 cents for sound quality, for sonic reasons. Sonic Hedgehog. Okay. Now we want to call our update function, which we haven't written yet, to update our GUI, use our GUI controls to update all the other values on our oscillators. Okay, that should be enough. Update from GUI. Okay. So we better write this update. We'll do that right at the end of the file, I think. Is it better to do it there? Is it better to do it near where it's used? Let's do it here. So this is going to be a void, and we're going to see nanosynth. Update. Okay. So let's just pop across to our nanosynth.h file, and we can see here are the GUI variables. So these are all set by the GUI that we've got. We've prototyped a GUI using RackAFX, and these are the values we set. So we've got waveforms for the oscillators, waveform for the LFO, we've got LFO modes, and we've got amplitudes and all that kind of stuff. So let's take this value for a start, the oscillator waveform. And over here what we can say is that oscillator 1, and we've got a member variable on that called waveform, if you remember, and we're going to set that equal to that GUI control. And oscillator 2, we're going to always have the same waveform for oscillator 2. Okay, and then we want to call update on both of those. Remember that they have their own update functions. So it's going to take the value of the sample rate and take the waveform. It's going to work out what to do. Update. Now we want to do the same kind of thing for LFO. So we're going to say that the LFO and the U waveform is going to equal. So over in the header file, our LFO waveform is here, and we've got an LFO1 waveform, because if we have more than one LFO, then we could run them with different waveforms. Then we want to set the amplitude. It's what we call the depth normally. I think the control calls it the depth. It's the amplitude of the waveform that we're using for the LFO, and that's a double. That's going to equal, we go over here, find out the amplitude. There it is, LFO1 amplitude. And then we want to do the frequency of the LFO. Oscillator frequency, and that's going to be the rate. So we've got slightly different terminology between low frequency oscillators and pitched oscillators. Amplitude is often called depth, frequency is often called rate. So that's the frequency of the oscillator. Now we want the depth. So we've done the depth. Now we want the mode. So which mode is it? Is it synchronized mode? Is it single shot mode, or is it free running? And I did explain the difference between those last time, but just to reiterate, a single shot oscillator. When you press the note, it will go through a single cycle, a single wave cycle, and stop. And so that's single shot. Synchronized means that whenever you're playing notes, it will always start from a phase angle of 0. So you play the note A, and your low frequency oscillator starts from a phase angle of 0 and goes through its waveform, and you play note B, it starts again at 0. Whereas a free running oscillator just carries on going up and down, and wherever you happen to be on the waveform when your note comes on, that's the value you get out of the LFO. So slightly different modes. And this will allow us to kind of experiment with that and see what it does. So there's the LFO mode, and now we want to call update on LFO1. Okay. So this is to update the C++ objects from the GUI controls. Okay, so the next one we're going to look at is ProcessAudioFrame, which is the next one here. So as it says, it's a fully normalized output, so we're going to output samples in the range -1 to +1, which is what we want. We have two different inputs. So if we're building an effect rather than originating waveforms, then obviously we have input buffers, we have output buffers as well, left and right channels. That's supposed to be output there, look of it to me. I think it's pointless changing it, but we'll give it a go. It's a spelling mistake on Mr. Perkle's side. Okay. So what do we need to do here? Right. So I don't think we need to do any of this. Let's comment that. Let's remove. What's the best thing to do? Should we just comment it out for now? Because that is really kind of passed through. That's passing an input buffer and an output buffer, isn't it? And we're actually originating our sounds. So we need a variable which we'll call dout, like we did before, and we'll initialize it to 0. So silence initially, and then we want to say, do we have a note on? So if m oscillator 1 dot m note on, which was the value we were using before, then we want to do stuff. So what do we want to do? We want to grab the output of our LFO, for example. So we want to sample from our LFO, so we'll do that first. So this is going to be a double value again. All our samples are floating point numbers. So D, what should we call LFO out? LFO1 out. We might have more than one. That's going to equal LFO1. LFO1, and that's going to be do oscillate, so we get a sample back. Do oscillate. and we're not going to pass the quad phase pointer into there, so it's going to be null. So it'll be set to null because in our LFO H file here, remember that it defaulted to null if we didn't pass it in. Okay, so we've got our LFO. Now we want to run our oscillators. So we're going to make oscillator 1. No, it's going to be a set. We set the modulation, so there should be a set method in here somewhere. Set frequency. I think that's it. Anyway, and there we pass in the LFO output, and we multiply that by our constant, which is the range, the modulation range. So I think it was called mod range. There we are. So that's all defined in our, I believe that's defined in our synthesizer. So it's two semitones. So it's going to range by 2 semitones. Where's that defined? I can't remember. In our oscillator.h. So these are the various constants that have been set up by our file that was provided for the project. Okay, so we've got that. So we're going to do the same thing for oscillator 2. So we set our modulation up. Then we want to update those oscillators using the update method, because we've changed the modulation. Oops. Okay, and then we want to basically get some sound. We want to sample out. So D out is going to equal. And what we're going to do, we're going to mix the two oscillators together equally. So 50% of oscillator 1, 50% of oscillator 2. So we're going to say 0.5 multiplied by M oscillator 1 do oscillate, and then we're going to add into that 50% of the output of oscillator 2. And remember, they would normally be producing exactly the same sample, so this would just produce the same that one oscillator would produce if we didn't mix together half and half. But this second one is going to be detuned by 2.5 cents. It's slightly different frequency. So that's that. So now we're going to, we've got an output buffer. So output buffer 0 there. We want that to our D out value. So this is very similar to the kind of stuff we've done before, working with Juice. Juice and RackAFX are remarkably similar in many ways. So now we need to know whether we're stereo or not. And we should have a number of channels. Sure, there's a value which says how many channels, so it's basically that there. I don't like having statements living on their own, so we get rid of that. Move it up here. Like that. Come on. And that's going to equal D out as well, because we, as I say, we are a mono synthesizer at the moment. So mono in, stereo out. And there's this one as well, isn't there? I'll put some brackets around that as well. So this code, where we have these two different ways of doing things, is pretty familiar. Okay. Let's see if we compile so far. Okay, we do. Okay, that's good. So what's next that we need to look at? So we've set up our, so we can get rid of all this code now, we don't need any of that. So this is basically where we render audio. This is the first time in all the code we've written where we're going to be able, hopefully at least, we should be able to hear something, because we're rendering audio to output channels, to output buffers. Alright then. User interface change is the next thing we need to do, and this should be fairly simple. Basically all we need to do is call update. Because we've built our own update function. So update, return true. That should be all we need to do. Okay, so now we get to kind of a bit more kind of the meatier side of it. Not meatier, but bits where we've been before, I guess we can say. We want note on and note off. So we've been in here. This is note on and note off. So this is us pressing keys on our MIDI controller keyboard. And you can see we've been in here before, and we've set up this guard clause, which makes sure that the channel, if we haven't got all channels being read, that we're picking the right channel up, and we've got our tracing. Okay, so what do we do? Well, basically, what we need to do here is to what we need to do here is actually we need to send our MIDI, our oscillators, the value of frequency they want to produce. Okay. Now, obviously, with the low frequency oscillator, that's set through the GUI, but with our pitched oscillators, the frequency depends on which note you're playing. Okay, we've got a table of MIDI notes and the frequencies that they correspond to. So, for example, I think A3 is 440 Hertz. Okay, so these values are all known about. So we've got a table of those built into our plugin constants and our synth functions, so we can use those. Okay, so it's pretty repetitive code, but so we're going to set the oscillator frequency. So there it is, oscillator frequency. So the FO is actually F0, so the frequency of our oscillator. So that's going to be equal to our MIDI frequency. We can look at the MIDI frequency table, which you've got. MIDI frequency table here. And we're going to index into that by the value of the MIDI note that's been played, and that is U MIDI note there. And we set the oscillator frequency for oscillator 2 in the same way, because they're always going to be the same in this particular model. And then we're going to call update on both of those, so we can go and pinch that code from elsewhere. That's probably quicker to write it, isn't it? I can't remember where it was. So we're just going to call update on those. os1.update and os2.update. Okay. Once we've set our frequency and we have updated all the other variables that depend upon the frequency used by calling the oscillator's update method, then we can play it. We can finally actually render some sound. So we're going to do the start oscillator method on each. So oscillator1 dot start oscillator, and we're going to do that for oscillator 2 and our low frequency oscillator. And this is the advantage of having this base class underpinning all our oscillators. It's quite simple then to call these things. Okay. So we've then got note off. MIDI note off. So we can come in here. Okay. So in here, we want to stop our oscillators, don't we? So that's fairly simple. If there's a start oscillator, there's a stop oscillator. So let's pinch this code, and we'll change this to stop. And let's build. So built. What I can't remember is getting this to. I don't remember having issues getting it to debug. So what I'm going to do, I think I'm going to stop it. I'm going to reload my project. I'm a bit confused about why it was having issues last time. So open project. No synth. We want to debug. Okay, so we're in debug mode. Wait, have we hit a breakpoint? Okay, now we're going to load it. I believe that's what we. Yeah, see, we got a problem here. I'm not sure what. Sorry00, thank you for the follow. Thank you very much. Have some electric Alf to celebrate your follow. This is a WebGL shader that one of the viewers of the stream, Pure Snable, created for us, and we're going to be doing a stream in the very near future, in the next couple of weeks, where Pure Snable is going to come on and teach us how to create shaders. So that should be quite exciting. So thank you very much for that follow. That's very, very kind of you. Okay, so why are we getting an issue with this? Unable to start program. So this was working fine when we didn't have all this oscillator code in it, so it should have just worked before. So I was slightly concerned that even when we hadn't wired up the oscillators, our synth code wasn't running. because it should have been enabled us to do exactly what we did last time, which was to use our MIDI keyboard and log all the various controls like the pitch bend wheel and mod wheel and the keys on and off. This is going to be a problem because solving this issue on stream is going to be pretty tricky. Basically, because I don't know what's changed. It's saying it's not a valid Win32 application. Maybe it's because I've somehow got it stuck in x64. Let's try that, and let's try building that instead. Okay, it's building. Okay, let's see if we can debug now. Oh, looks happier now. So let's have some alphas happy. Okay, now we're going to load our plugin. And here's our controls. So our oscillator is going to produce sine waves, and so is our LFO. We're in synchronous mode, a rate of 0.5 Hertz for our LFO, and our depth we'll set our depth to half, shall we? As close to half as we can get. There we are. Okay, so I'm going to just stop the music for a second. Let's hold that. I'm going to reach across from my MIDI keyboard and see what happens. So we're getting a response in terms of the MIDI values being recorded there, but there's nothing audible to us. Let's make sure. Let's just unload our plugin. And we'll load an audio file, make sure we can actually hear audio files. Let's play that. So we haven't got, for some reason, my audio setup is not happy. Let's try again. Valid device. It's one of these things that I was kind of concerned about because OBS has got part of my audio setup. I wonder if that's the problem. So this is, let's make a note of what it's actually set to, because this is, as far as I'm concerned, a working setup. So it's Realtek. Oops. Realtek HD audio mic input WDM 1 and 2. So what happens if I change that? Change it to the Razer Kaio. I'm not getting any sounds, so that's a bit disappointing. I think I'm going to have to take that off stream to see if I get sounds when I'm not streaming, because that is a bit odd because it was working. This OpenStream invalid device is saying something it doesn't like about my audio setup. Let's load the plugin again. So we can see we're actually getting values that are being printed out. Okay, so we know that we're getting MIDI messages going in. So what we can do, even though we're not hearing anything, we can go and place a breakpoint here. I'm just going to lean across and press a MIDI key. So we've hit enter here. There's our frequencies being set up. We've updated our oscillators. And we can step into start oscillator. And it sets note on is true. Okay, so we can't go any further with that debugging, but we do know we're hitting inside our method. So I think the next stage for me there is to take that off stream and figure out if I'm getting sounds when I'm not streaming. Because I think that's the problem. I think OBS has grabbed all my audio, which is reasonable, but inconvenient for this particular stream. I would have thought it should play it through my desktop channel. So these are all working nicely. What I'm going to do is just bring my keyboard within easier reach. So this is my keyboard. It's a Roland A49. It's quite a lovely little MIDI controller, not expensive, because I couldn't afford a really expensive one, but this is a really nice one. So we're hitting breakpoints okay, so I'm pretty convinced the code is actually working as we would expect. I'm interested in the fact that log MIDI, let's just stop it a second. Let's go up to the top. I'm going to comment out that. I'm going to then unload, which is I forgot last time, unload our plugin, rebuild it. And we get some music back. We'll debug. So we have these wonderful buttons, make VST and make AU, which is we will need to leave to the end. This is making plugins which are portable into different digital audio workstations. So I've got Ableton Lite, and I've also got the full version of Reaper. So the end game of this is to have a whole range of different types of synths which we can use within as virtual instruments within our DAWs. But yeah, so we've got rid of the let's load it in. So we got rid of the messages now, but it's still not making any sounds, and I'm pretty sure it must be because I wonder what the amplitude of our waves are. Where can we go and find that out? In here, do oscillate. We come to the bottom here, and we're going to multiply our output by. So let's put a breakpoint right there. Play a note. Interesting. anything there, are we? Are we still running, aren't we? The do oscillate. Let's pop a breakpoint there. Do oscillate doesn't seem to be being called. Okay, well that's something different than I expected. So let's have a look at that. With a sine wave, blah blah blah. If we go to do oscillate's probably started already, hasn't it? So we need to be in here, and let's unload our plugin, and let's find where we call do oscillate. Here. Let's put a breakpoint there. We'll reload our plugin. So we're not hitting that. Stop again, try again. So what we'll do is we'll hit debug and hit load. So we're never getting into ProcessAudioFrame. Okay. So let's put my keyboard away. My drinks. I need a drink at this point. Right. Let's go through and have a look. That's all the code we've written in here. So we know we've got our oscillators instantiated, so that seems fine. So the next thing we need to do was prepare for play. And that's here. So we've set up our sample rates as we expect, detuned and run update. I wonder what that's doing. Let's try a few things out, see if we can get anywhere with it. Let's pop a breakpoint there, and we'll debug. Let's go back to our thinking phase, shall we? So we've hit a breakpoint here. So I think that invalid device is telling me that our audio is not right. So I think the best thing for me to do at this stage is to find someone else to raid, and then I'm going to have to go and think about this and see if I can figure out how to share the audio. I think it's because OBS has got me audio. I think that's what it is. So let's unload and stop debugging. I think I'm going to have to, what I'm going to do is to push all this up into GitHub. So let's commit our changes for today. Episode 59. Push that up to GitHub. So if you want to go and look at the code or play around with it, then it's there, and you can also follow along with the project if you wish. If you get yourself a copy of RackAFX version 6. What I'm going to do is find someone to raid and go and think about this. And you never know, I may pop back up if I can figure it out, or I might come back on Sunday and see what we can do then. But it depends how long it takes me to figure out what on earth is going on. So who can we raid? So let's go and have a look. Oh, we got C# Fritz, and we got Calvin Allen. 115 against 2. So we'll go and see if we can go and raid Calvin, shall we? So I'm sorry about not getting very far with that, but hopefully it shouldn't take too long to figure out. And if it is a problem with OBS grabbing my audio channels, then I'll have to figure another way of doing this. So it might take a little while to figure out. So thanks for viewing, and I will see you again very shortly in the next couple of hours, or perhaps the next couple of days, when I've figured out what the problem is. So take care everyone, and I'll see you then. We're raiding now over to Calvin.